Good day and welcome. This is not the National Geographic Channel, but I'll be your host, Robert McFarlane. I studied environmental science at Rhodes University and have guest lectured for the Habitable Planet workshop twice before on 3 different topics. I currently live and work in South Korea in between traveling. Let's get started, shall we? My topic will be the origins of life, particularly abiogenesis as well as panspermia. Let's look at the table of contents. First I'll ask, if you want to make an apple pie from scratch, how big is space? Where does space come from? Where do the stars, planets, and galaxies come from? Then I'll speak about our special planet, the conditions for life, and the theories for the origin of life. But first, let's have a look from one of my favorite scientists, Carl Sagan. He says, if you wish to make an apple pie from scratch, you must first invent the universe. What can he possibly mean by this? Well, I think what Carl Sagan is trying to say is, you can't have something in nothing. Therefore, if you want to have a planet that is habitable, stars, galaxies, you first need to invent a universe. So now that we've got our universe, let's get into the next question. How big is it? Well, Douglas Adams says space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road, but that's just peanuts compared to space. We live in the Milky Way galaxy. We get our energy from one of the stars in this galaxy. There are over 100 billion stars in the Milky Way galaxy. But that's nothing. There are over 140 billion galaxies in the universe according to scientists. Try to wrap your head around how phenomenally big the numbers we are talking about really are. So, where does it always come from? For centuries, scientists thought it always existed in a largely unchanging form, running like clockwork, thanks to the laws of physics. But in 1927, a Belgian priest and scientist, Georges Lemaitre, proposed the universe began as a large, pregnant, primeval atom. It exploded and sent out all the smaller atoms that we see today. However, this idea went largely unnoticed. Until 1929, that is. In 1929, astronomer Edwin Hubble, who the Hubble telescope is named after, discovered that the universe isn't static, but is in fact expanding. Because of this, some scientists believe if you rewinded far back enough in time, the universe should have existed as a tiny, dense point in space. However, critics dismiss this. In fact, astronomer Fred Hoyle sarcastically called this concept the Big Bang Theory. But this name got adopted by the scientists who believed this theory. Undeterred by skeptics, scientists Ralph Alpher, George Gamow, and Robert Herman predicted that if there had been a Big Bang, there should be a faint afterglow lingering somewhere in the universe, and we should theoretically be able to detect it. However, finding this faint afterglow took one of the biggest instances of luck ever to have occurred in science. One day, the astronomers Arno Penzias and Robert Wilson were struggling to tune in to the microwave signals transmitted by the Milky Way. Their radio antenna kept picking up a persistent, mysterious, weak hiss. Static. First, they thought it might come from a nearby military radar, but this wasn't the case. Then they thought it could be the cars on the freeway, but again, they proved that it wasn't. Maybe it was the side effects from nuclear testing, which was very common at the time, but again, they found that this was not the case. Eventually, they even thought that it could be the fact that pigeons were pooping and living on their antenna. So they booted the pigeons out, cleaned up the poop, dismantled the antenna, rebuilt it, but still they could hear this faint hiss, the static in the background that they had heard before. What they had accidentally discovered was cosmic microwave background radiation. This was the faint whisper that the scientists had predicted you would be able to hear if the Big Bang had in fact happened. So, if the Big Bang theory is true, how did it lead to all of the planets, stars, and galaxies we see today? Thanks to calculations, observations from telescopes on Earth, and probes in space, our best explanation is this. Around 13.8 billion years ago, all the matter in the universe emerged from a single minute point in one violent burst. This expanded at incredible speed and at extremely high temperature, doubling in size every 10 to the power of minus 34 seconds. Look at all those zeros. That is an incredible rate of expansion. Creating space as it rapidly inflated, within a tiny fraction of a second, gravity and all the other forces were formed. Energy changed into particles of matter and antimatter, which mostly destroyed each other. Fortunately for us, some matter survived. Protons and neutrons started forming in the first seconds. Within minutes, the protons and neutrons started fusing, creating hydrogen and helium nuclei. After 300,000 years, nuclei could finally capture electrons to form atoms, filling the universe with clouds of helium and hydrogen gas. After about 380,000 years, it left behind a bath of photons. This was the cosmic microwave background Penzias and Wilson accidentally detected. Contained in this were tiny ripples of matter that were stretched to enormous size during inflation. In turn, these became the seeds for the galaxies and galactic clusters we see today. Phew! Now that we've got that out of the way, let's have a quick side note before we dive into the formation of our Earth and how life began. We have seen how the universe, galaxies, and stars were formed, but I want to explain why this is important to us and our lives. One of my favorite quotes is again from Carl Sagan. He says, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were all made in the interiors of collapsing stars. We are made of star stuff." The reason this is true is because the heavier elements did not exist when the universe first formed. The heavier elements could only be forged in the giant furnaces of stars through fusion. These heavier elements could only be expelled by the death of stars. When they collapsed and they exploded, they sent out their heavy elements into the universe. So, the nitrogen in your DNA, the calcium in our teeth and bones, the iron in our blood, the carbon that we are made of, all comes from ancient dead stars. And, interestingly, the carbon, nitrogen, and calcium in your left hand probably comes from a different star than the carbon, nitrogen, and calcium in your right hand. Stars died so that we may live. We are a way for the universe to know ourselves. The cosmos is within us. We're made of star stuff. We are a way for the cosmos to know itself. Isn't that absolutely incredible? Okay, back to the origins of life. Earth is shaped and molded by life. In this way, it is unique as far as we know. But how did this happen? Earth is now home to about 7 billion people. But when it was formed about 4.5 billion years ago, it was a violent place. So hostile. It's hard to believe that life could ever begin here. Covered in lava and smothered in poisonous, noxious gases. Nothing like the Earth we know today. It was a planet plagued by catastrophe. Very shortly after the Earth formed, it melted and reformed. To make things worse, a planet about the size of Mars slammed into Earth shortly after it was formed. This gave birth to the Moon. But shortly after these cataclysmic events, the most radical change in Earth's history occurred: the origins of life. So, how did life begin? Throughout the ages, people have had many theories. One of my personal favorites being from the 17th century scientist who wrote down a recipe, a crazy recipe, for creating life from scratch. He said, take a dirty cloth, put it in a jar, add wheat, and according to his recipe, after fermenting for 21 days, mice would appear, fully formed. We all know life doesn't form this way, but in Earth's early years, life did form out of non-living ingredients. Early Earth was not a Garden of Eden. It was very hostile. No clear blue oceans, but rather they were olive green. No plants, no life at all. The young sun was weaker than it is today. Its light barely penetrated the atmosphere of carbon dioxide mixed with hydrogen sulfide. Since the atmosphere was thicker and dominated by CO2, the Earth had a red tinge to it. For hundreds of thousands of years, comets pounded our planet. This time was known as the heavy bombardment. Though this may have been a hellish environment that seems likely nothing could have lived, we now know today of things called extremophiles, deep in mines in South Africa, or inside nuclear reactors, or geysers. We find extremophiles who live in the harshest of conditions, adapting and changing and thriving off of the most unlikely sources for life. But where did life come from? For more than a century, scientists have known that life is the result of chemistry, a combination of just the right ingredients in just the right amounts. We now know it's not things like dirty cloths and wheat. The ingredients are actually much, much simpler. All living things, from bacteria to mice, to you and me, are from a small group of elements: hydrogen, oxygen, carbon, and nitrogen. 4 of the most common elements in the universe. Combined in just the right way, these are the fundamental ingredients for life. And carbon is the star of the show. Carbon is abundant in the universe, and what makes it special is the kind of bonds it makes, both with itself and other elements. We know of no other atom that has the flexibility that carbon has to form diverse types of compounds. The idea that life could have started when carbon and other ingredients combined in the harsh conditions of early Earth was first put to the test in the 1950s by a young student named Stanley Miller. Miller made a setup of flasks and tubes with gases they thought were abundant in Earth's early atmosphere, and had it connected to another flask with water to represent the oceans. Then he did something brilliant. He put an electronic charge through it to simulate lightning going on during the early atmosphere. After several days of sitting, there was a brown goo all over the flask. When he analyzed what was in the flask, he discovered he had amino acids, the simple yet essential building blocks of cells and proteins, from nothing more than unliving chemicals, the vital ingredients of all living things. This was headline news around the world, and the 23-year-old scientist became famous overnight and jump-started the scientific race for the origins of life. Life really is chemistry. In fact, it is a chemistry that when you get the recipe right, it goes fairly quickly.
What took you so long?
This recipe is hotly debated today, and most scientists now believe the conditions on early Earth were very different from the conditions in Miller's experiments. However, life may have started even earlier than thought, perhaps during the bombardment. Evidence in some of the oldest rocks in the world found in West Greenland, rocks that are between 3.7 and 3.9 billion years old, rocks that are so old that any evidence of microfossils will have been destroyed. But they have found carbon evidence of simple life. If it arrived so early, life was lucky to miss the biggest cataclysm of all time, when the Mars-sized planet hit our Earth. The outer layers of our planet were vaporized, the debris formed into the moon. This impact would have destroyed any building blocks of life. This gives rise to speculation that the ingredients to life didn't form on Earth, but were delivered special delivery from outer space. This is not as absurd as it sounds. Space is not very far away. In fact, it is about 20 kilometers up. That is very close, and space is huge. A scientist named Don Browning designed an experiment to test this. There are more than 40,000 tons of bits of comets, asteroids, and space dust that hit the Earth each year. Most are less than a millimeter in size. To see if this shower of space dust contained the ingredients for life, Browning needed to get samples uncontaminated by Earth's atmosphere. To get just a few micrograms of dust, he commissioned a former spy plane to fly to the outer reaches of Earth's atmosphere, and he attached sticky pads to it to catch the dust, sort of like the fly paper you use to catch flies. They then sliced the space dust particles to thinner than 1/10 of the width of a human hair and analyzed them. They discovered these tiny particles are rich in the seeds of life. This extraterrestrial dust isn't the only possible source of life's ingredients. In a region of space called the asteroid belt are huge amounts of debris left over from the formation of our solar system. Sometimes chunks of debris containing metal and rock fall to Earth, bringing surprising gifts. One such meteorite landed in the Australian town of Murchison in 1969. They found amino acids in this meteorite, the building blocks of life we were speaking of earlier. It was the first time that a complex organic compound had ever been found in material from space. If meteorites like it were common, perhaps they had delivered large quantities of the building blocks of life to Earth. More than 70 kinds of amino acids have been found in meteorites. Even bigger comets made of dust and ice have hit the Earth, some the size of mountains. This could have been a more efficient way of bringing the amino acids and building blocks of life to our planet. Some people have argued that the speed and impact would destroy any such amino acids, so an experiment was done to see if this was the case. A scientist, Jennifer Blank, built a huge gun. She built this gun to simulate the immense speed and pressure that are unleashed when a comet crashes to Earth. They wanted to see if the material and the amino acids would survive or break down to smaller parts. They expected it to break down, but they hoped some would survive. What they found was far more interesting. The pressures they produced were massive for the experiment. If you go to the bottom of the ocean, you are only a few hundred atmospheres of pressure. They were generating hundreds of thousands of atmospheres of pressure to simulate a comet striking Earth. They wanted to see if the building blocks of life could survive a crash landing to Earth. Not only did the amino acids survive the colossal impact, but they had transformed into a new, more complex compound called peptides. They went from small compounds to big compounds. This illustrated that the energy from the impact could in fact be used to grow larger molecules from the simplest building blocks of life. Peptides link together to form larger building blocks, proteins, which make up all the cells in our bodies and the cells of living things. One of the big mysteries in science, however, is the leap from the simple building blocks to living animals, complete with DNA for replication. This is staggeringly complex, and no one knows how this process started or what course it took, and no one has succeeded in doing this in a laboratory yet. However, who knows? Perhaps one of our very own Planeteers could go and solve this mystery and advance science. I hope you have all enjoyed our talk on the origins of life, and it has motivated you to go and investigate it more deeply and learn more about it. I'll close with a clip from an incredibly scientific movie, Jurassic Park.
The history of evolution has taught us that life will not be contained. Life breaks free, it expands to new territories, and crashes through barriers painfully, maybe even dangerously, but well, there it is. There it is. You're implying that a group composed entirely of female animals will breed? No, I'm simply saying that life finds a way.
Indeed it does. Life finds a way. Good luck to you all. I hope you enjoyed this. Thank you and enjoy the rest of your course. Goodbye.